Welcome to another edition of the Henstitute. Here we are going to look at a box or a block here that's going to slide down this incline, and so it's going to move in this direction and it's going to run into this spring. So I put some extra little pieces on here. We've got the MegaWork energy equation up here at the top. And the spring, initially it has no compression. And I don't know if you can see it in here, but I give you the spring constant of 100 newtons per meter. We've got the mass of the block. It's originally not moving, but eventually it is going to be moving. But the idea of this problem is if it starts 1 meter away from this spring, and the spring is not compressed initially, it's going to eventually hit it and compress it. What I want to know is how much total compression is it going to apply on that. And then just to make this a little bit easier, we're going to assume that this is a frictionless incline. So we're going to have mu k be 0, and theta is going to equal 45 degrees. So this is a 45-degree incline. And last but not least, this block is going to start 1 meter away from the spring. So as I kind of think about this, what kind of pieces can I get rid of? The first instinct is, since I have no friction happening down here, there's no force acting on this block except for gravity and except for the spring. And so those forces are already caught up in my elastic potential energy and my gravitational, so I don't actually have any external work being done. If this was not equal to 0, so if this was not a frictionless surface, then we would have some work being done as it slid this 1 meter, but we don't actually have to worry about it. The other one that always throws people off again is this kinetic energy. We know we've got an initial kinetic energy of 0, but the idea is, oh, this is going to be moving, this is going to be moving. So don't we have to take into account kinetic energy? That's true, except we're looking for the maximum compression of this thing. What is going to be the final velocity of this thing after it hits this and compresses? It's going to be 0 again. So we've got initial and final that's equal to 0. We have no change in kinetic energy. Do we have a change in gravitational potential energy? Well, really that's asking, do I have a change in height? Because it's mass times gravity times my final height minus my initial height. And I would say, yes, we definitely do. Now, it's a little bit weird here because my heights have to be measured a little bit different. Since it looks like everything's kind of happening with this bottom corner of the block, that's what I'm going to use. It initially is here, so there's my initial position, and its final position is going to be here. So really what I'm going to end up doing is I'm going to kind of draw a line here, a little horizontal line. And what we're going to be looking at is how high up is it here and how high up is it here. Now there's a couple of different ways to do this, and that makes it a little more difficult. Probably the easiest is to start with the initial place of the spring like we talked about before, and so I would actually make this kind of my height of 0. And if that's my height of 0, then when we're actually trying to figure this out, we should be able to measure these other heights. But really, what I'd be looking at is this little height and this height right here. So in essence, what I've got to start off with is I have a little triangle here. So my initial height is this, and my final height is actually going to be this little piece. So I have both of those, and I'm going to keep those in. Last but not least, I have my elastic potential energy. Do I have a spring? You betcha, I have a spring. So I have 1/2 K times my final compression squared minus my initial compression squared. But to make it a little bit easier before we even start this, my initial compression is 0. So I'm just going to eliminate that one. I'm just going to go ahead and erase it. But I just wanted to kind of remind us that we do actually have it in there. And just to keep everything else, I'm going to erase these. We have those pieces kind of disappearing. But remember, this has to still equal something. So really what we've got is these two things equal 0, which really means that since this equals 0, I can take these two quantities and set them equal to each other as long as I kind of flip one of them. I have to make one of them negative. So what I'm going to end up with is I'm going to end up with a mass times gravity times my final height minus my initial height here. And that's got to equal, what I'll do is I'll put a negative sign on this, a minus 1/2 k times my xf squared. Now, unfortunately, this one's going to be kind of like our other one where we had the block dropping onto the spring. So this is very similar to that kind of concept when I actually have it working. So we're going to end up having x in two different places. Remembering our nice little right triangle stuff here, we know that my initial height here is the side. We know this angle here would still be my 45 degrees, just like this little angle would be 45 degrees. And so my XF and my HF are related. My initial height and that 1 are related. So the 1 is actually the hypotenuse of the triangle, and we're trying to find that initial height. And so if I think about it, it's the opposite and the adjacent. So I'm going to end up using a little bit of sign here. So my initial height is actually going to be equal to the hypotenuse, which is 1, times the sine of this angle, this 45 degrees, because the sine of the angle would be opposite over hypotenuse, and this hypotenuse happens to be the 1, because that's how far along here. And then my little HF is actually going to be the hypotenuse, which is going to be my XF. This one's going to be equal to XF times the sine of 45 degrees. But since it's going to actually be going down that much, remember we've got to actually make this negative, so I'm going to put a negative sign on there. So I'm going to replace some of these numbers. We've got our mass, which is 5. We've got gravity, which is 9.8. And then for my final height, I know that that's going to be a minus XF times the sine of 45 degrees. And then my initial height is going to be 1 times the sine of 45 degrees. So really what has happened is this little sine of 45 degrees, the sine of the angle is popped in like we didn't have it before. And then all of that should equal my minus 1/2 times 100 times my final compression squared. So kind of simplifying some of these things, I'm just going to switch this over and let's just draw this all in purple here. 5 times 9.8, this is actually supposed to be a 9.8, is going to be 49. So I have a 49 times this quantity in here. So I really have a 49 that's going to multiply by the negative XF, and then times the sine of 45 degrees. Well, the sine of 45 degrees, we know, is our square root of 2 over 2. And so over here, I have a minus square root of 2 over 2. So I could actually pull that square root of 2 over 2 out. Let me grab a calculator here so I can actually calculate it. Sure enough, the 49 times the square root of 2 over 2 is going to end up being 34.648, some other decimals. So that's going to be times so it's going to be a minus an XF, and then also a minus 34.648, which is just that number. And then this should all equal half of 100 is 50, a negative 50 times XF squared. So look, it's going to be quadratic again. So we'll probably bring this over to the other side. So this would be 50 times XF squared minus my 34.648 times XF minus my 34.648, and that would all equal 0. So I would pull out my calculator and try to use the quadratic formula on this. Okay, finishing things out down here. When I typed it up on my calculator, I got 1.248, and then I'm negative 0.555, blah, blah, blah. And again, your instinct is you want to make that negative probably be, because you're like, oh, being compressed, it's compressed, that should be the negative. But the negative actually is just the negative solution to that quadratic equation. That's not what we want. We have already taken into account our negative up here when we made that height negative. All of our compressions or stretches should be positive. So I don't want that one, so I'm going to get rid of that one. What we want to do is keep this one. So my final compression here should be this, and let's see, I've got 1 sig fig and 2 sig figs and 2 sig figs. Let's just go ahead and keep 2, so I'm going to say 1.2 meters. So if this 5 kilogram block slid from 1 meter up on the ramp into this spring, it would compress the spring 1.2 meters. If you notice in this particular equation here, we have a nice direct relationship between mass and that compression. So if it was twice as massive, it would not actually be twice the compression. It would actually be the square root of 2 times that compression. But if you notice that you had twice the compression, that would actually be 4 times the mass that would be causing that. We have a direct relationship between our spring constant here and the heights. All those things kind of coming into account. It's kind of neat to see how things are related. Very similar to our previous problem. The other one that we might have in this one is a reverse of this. What if I pulled this back and I launched it up the incline and I tried to figure out how fast it was going or something like that? There we might actually have some kinetic energy, or if this incline had some friction to it, we could have some work being done. So it could be a more complicated problem. We'll probably stick more with this easier stuff. This has been an edition of the Henstitute. I hope you enjoyed.